Hello friends, the next topic of BJT is modes of operation of BJT, different modes, carrier distribution. I repeat, modes of operation and minority carrier distribution. I'll be taking one example. You can take any of this. So I'll be taking the example of P and P type. So we have P and P, or you can take NPN, that's your choice. Fine. So when you have P and P transistors, so first a normal active mode. That is first mode of operation, normal active mode. In normal active mode, this is emitter junction, this is the collector junction. A BJT is said to be in normal active mode when emitter junction is forward biased and collector junction is reverse biased. So in this mode of operation, emitter junction is forward biased and the collector junction, that is JC, is reverse biased. That is your first mode of operation. Fine. That is your first mode of operation, normal mode. Let us see the distribution. This junction is forward biased, this junction is reverse biased. Remember, if you remember the PN junction diode, the concentration of minority carriers is maximum at the edge in case of forward biased PN junction, and concentration of minority carriers becomes zero at the edge of depletion layer in case of reverse biased PN junction. So on this side, if it is P, what are the minority carriers? That is electrons. On this side it is N, so what are the minority carriers? That is holes. On this side, what are the minority carriers? That is electrons. So at steady state, I will be saying, I'll be assuming the concentration is like this. On this side I have minority carriers as electrons, so I will be saying the concentration of electrons on emitter side at steady state, Ne naught. Ne naught stands for concentration of electrons in emitter at thermal equilibrium. Similarly, say concentration of holes in base region Pb at thermal equilibrium is Pb naught. Similarly, on this side, concentration of electrons in collector region at thermal equilibrium is Nc naught. But when the junction is forward biased, this concentration will be varying like this. It will be reducing exponentially after injection. When it is forward biased, electrons from base will be injected in emitter, and after injection it will be diffusing through the emitter. So after diffusion, concentration of the charge carriers reduces exponentially. So that is how it is going to vary. Similarly, when holes from emitter side are injected into base, these becomes minority carriers there, but since holes are having high concentration, so concentrations of holes will be high, but it will be reducing exponentially and becomes zero where at the edge of the depletion layer in the base region. That's how it varies. But here it will be more. Why? Because the concentration here is high. Doping concentration on emitter side was high, so minority carrier concentration is higher at this point as compared to this point region, because base was having less concentration. So when electrons from base are injected, so it has smaller level. Now let us talk about collector. On collector side, at the edge it has to be zero. Why? Because in reverse bias junction the concentration is zero at the edge and it will be increasing when you move, and finally it will become equal to Nc naught. So that is how it is going to vary. In which mode? In case of normal active mode, emitter junction is forward bias, it is maximum at this on this side, maximum on this side, this is zero at reverse, zero at this. That is how the minority carrier concentration varies in normal active mode. Then I have the inverse active mode. The inverse active mode is just reverse of it. That is, your emitter junction is reverse biased and collector junction is forward biased. That is forward biased. So operation seems to be similar, but there is a difference. What is the difference? Collector is forward biased, there is no problem. Emitter is reverse biased. When emitter junction is reverse biased, what will happen? There will be heat generation at the emitter junction, but emitter junction is not designed for dissipation of heat at the environment. Otherwise, what should be there? The size of the emitter should be large so that heat is dissipated to the environment. But in fact, collector is designed for that. Collector size is more so that the collector junction can be reverse biased when it is operated as an amplifier in active mode, in forward active mode, normal active mode. But when it is operated in reverse active mode, emitter junction is reverse biased, but emitter is not having that much size to dissipate the heat to the environment. So what will happen? There will be generation of heat at the emitter junction which is not sufficiently dissipated to the environment. Temperature of the emitter junction will go on increasing, and finally it will damage the emitter thermally, emitter junction thermally, and your device will be damaged. So a BJT is not operated in inverse active mode, but just for understanding point of view of BJT as an operation, as an amplifier, we will be talking about inverse active mode as well, but BJT is never operated in inverse active mode. Fine. So it will be just reverse of that, whatever you have discussed. Here, this is the concentration level on collector side, this is the concentration level on base side, this is the concentration level on this. Why it is like this? Because this is lightly doped, so magnetic carrier concentration is a little higher. This is moderately doped, it will be little higher, it will be smaller in case of the emitter, because it is having high level of doping. When it is having high level of doping, the magnetic carrier concentration will be smaller. That is how it is drawn. Fine. So here it will be like this. The concentration here is like this. Concentration is varying like this. Concentration is varying like this. It will be 0, and concentration will be varying like this. Just reverse of this, that's what you are going to have. So this is concentration of holes in the base region, concentration of electrons in the emitter region, concentration of holes in base region, concentration of electrons in collector region. Fine, that's how you have. Then third mode of operation is cutoff mode. Cutoff mode is basically the mode where both emitter and collector junctions are reverse biased. When junctions are reverse biased, I have already explained the concentration of the minority carriers at the edge of the depletion layer becomes 0. So on this side, if you draw the concentration of the minority carriers at thermal equilibrium, it will be increasing like this, it will be like this, it will be increasing like this. So on both sides it is 0. That is how the concentration of minority carriers in cutoff mode will be varying across the regions of the transistor. Fine. So this is emitter side, I told. This is collector side. Fine. Now let us talk about the third mode, that is your saturation mode. And what is the saturation mode? In this mode of operation, both emitter junction and collector junction are forward biased. When emitter and collector junction are forward biased, so concentration will be maximum at the junction. So here concentration is maximum, this is steady state level, this is steady state level, this is steady state level, right? So it will be like this, concentration is maximum but it will be reducing exponentially. Concentration is maximum here but it will be reducing exponentially, maybe like this, and concentration here is maximum but it will be reducing like this. Here it is reducing because this side was having higher concentration, this was having less concentration, so from this side to this side it will be reducing little. So that is how the variation of concentration will be taking place in case of saturation mode of operation. So there are how many modes in total? 4 modes. Forward active, where emitter junction is forward biased. There are questions on this, please do remember that. Plenty of questions. about the biasing of junctions in different modes of operation. Plenty of questions in engineering services, and there are questions in GATE 1 mark on whatever I am discussing. So forward active mode or normal active mode, the emitter junction is forward biased, collector junction is reverse biased. Then inverse active mode, these are the two modes where it behaves like an amplifier, in forward active and inverse active. But BJT is not using inverse active. I have already given you the reason, because there is a possibility of the thermal damage of the emitter junction, because that is not designed for sufficient heat dissipation. So the BJT is used as an amplifier in normal active mode of operation. Second is your inverse active mode, similar to your forward active. Here collector junction is forward bias, emitter junction is reverse bias, but BJT is not operated in inverse active mode. Third mode is cutoff mode, where both emitter junction and collector junctions are reverse biased. When both junctions are reverse biased, the current through the device is negligible. Therefore, BJT behaves like an open switch. In which mode? In cutoff mode of operation. Third is saturation mode. You can see the current through all the layers is maximum. So the BJT operates in saturation mode when both junctions are forward biased, current to the device is large, and device behaves like a closed switch. So for switching operation, BJT is flipped between two, cutoff region and saturation region for switching operation. And for amplifier operation, it is operated in normal active mode of operation. So I hope the concept how different modes are there in BJT, and there are a lot of questions on whatever I discussed. So I hope the concept is clear. So we'll be talking about BJT as an amplifier at later stage, but you should remember the different modes of operation. You should learn the topic bit by bit. Your understanding will be strong, your concepts will be strong. So just wait for my next video. I'll be taking the next topic, that is energy band diagram in BJT, and that is in normal active mode of operation. And just wait for my next video to come. Thank you for watching.